Jeez, I forgot to do my volume check. Getting a little cover for this mic soon. That'll be nice. Here. Let's listen. Alright, sounds good. Then Twitch, are you working? Yep. Alright, let's change the title here. Should we Google's? Isn't this a quantum computer? Yep. Alright. Throw some buzzwords up in that. That'll be good. Alright. So tonight I'm gonna take a little detour from the explainer thing. I think I'm gonna try doing this kind of thing during these streams, which is just reading through a paper and trying to give in addition to just reading the paper, trying to also give some amount of background where I can. I am not extremely strong with quantum computing. I, do have a degree in physics, and I also did a little bit of research in like quantum information theory, which is kind of related to quantum computing, but it's not the same thing. However, yeah, I mean, I know a little bit, so I'm hoping that I can at least, get through this paper a little bit to some degree and give some idea of what's going on here. So, I'll give that a shot. All right. Let's pop this open. So this paper is from about a week ago, and it's about the observation of a time crystal in eigenstate order on a quantum processor. So Google has these low number of qubit quantum processors right now, and they apparently managed to program a time crystal, basically, is my understanding of this paper. Which, cool, I don't actually know that much about time crystals. Just from the name, sounds pretty, straightforward what it is. It's like a system that, a crystal is of course, like, normally when we say crystal, what we mean is there's some like repeating structure from some like molecules or whatever in space. So like normally some like 3D structure, like an ice cube or whatever, has a crystalline structure. All the water molecules are like in very specific places, and there's like a symmetry because you can, if you have the same structure, just repeating, there's like, it's the same structure everywhere. That's called the symmetry. You can be a little bit more precise than that, but that's the right intuition. So I'm pretty sure time crystal is just a crystal where you also have it repeating in time. So you have some system that basically, if you go through time, the system returns to its original state. So the way a regular crystal, like the way that the crystals that you've thought about throughout your entire life work, or that if you move some distance in space, you end up with the same structure around you. You end up kind of in the same state. And time crystal, I'm pretty sure, is just if you move in time, you end up back at the same state. So that doesn't actually sound that crazy to me. Like, so what? But hopefully this paper will give some motivation. And it seemed like people thought this was cool. So yeah, let's go through it and see what we can pick up. So quantum many-body systems display rich phase structures in the low-temperature equilibrium states. However, much of nature is not in thermal equilibrium. Remarkably, it was recently predicted that out-of-equilibrium systems can exhibit novel dynamical phases that may otherwise be forbidden by equilibrium thermodynamics, a pragmatic example being the discrete time crystal. All right, so already I have no idea what this is talking about. So nature not in thermal equilibrium. Okay, by that, remarkably, it was recently predicted that out of equilibrium systems can exhibit novel dynamical phases. So I guess I don't have enough of a condensed matter background to know what novel dynamical phases means. They do have references here, but let's see if we can just push through. So probably this means, there's some exhibit novel dynamical phases. Yeah, I'm not used to thinking that way, but phases are basically relationships between quantum states, very roughly. So something going on between the relationships between quantum states that otherwise are forbidden by equilibrium thermodynamics. So I'm not really sure immediately what would be forbidden by equilibrium thermodynamics. So but this is basically just saying that when the systems are equilibrium states are states where things won't change anymore. So there's a lot of states that your system can be in where as time evolves, that state has to change. Like for instance, if you're in a system with a really high energy state, the energy of the system normally will decay towards a lower energy state, and then that low energy state becomes your equilibrium solution after you've given off all the energy, something like that. So right, so something about these, so you can imagine that equilibrium systems, because they always kind of stay the same, have very specific properties that are going to be different than the general evolution of arbitrary states. Okay, excuse me. So whatever they're saying, it's apparently surprising or something. A paradigmatic example being the discrete time crystal. All right. Concretely, dynamical phases can be defined in periodically driven many-body localized systems via the concept of eigenstate order. In eigenstate ordered phases, the entire many-body spectrum exhibits quantum correlations and long-range order. In eigenstate ordered phases, the entire many-body spectrum exhibits quantum correlations and long-range order. Okay. With characteristic signatures in late-time dynamics from all initial states. With characteristic signatures in late-time dynamics from the entire many-body spectrum exhibits quantum correlations. Okay, so normally in a quantum system, you have correlations between particles that are really close to each other. And I know one example of places where you can have really long-range correlations, I believe, don't quote me on this, but are in superconductors. So I think in a superconductor, the electrons end up having correlations with electrons that are really far away. But that's not normal in most systems. In most systems that we know about, there are, we have to get down really small into the system. You have to look at single atoms or single electrons or something. That kind of size range to get quantum correlations. So quantum correlations means entanglement. Okay. With characteristic signatures in late-time dynamics from all initial states. Late-time dynamics. So presumably this means that after a long time has passed, there's some correlations or certain things that will be true about any initial state in eigenstate ordered phases. Concretely, dynamical phases can be defined in periodically driven many-body localized systems by a concept of eigenstate order. Okay, so I don't know what this is. It sounds like they're going to explain what that is inside, so I'm going to punt on that for now. Let's keep going. It is, however, challenging to experimentally distinguish such stable phases from transient phenomena. However, challenging to experimentally distinguish a stable phase from transient phenomena, wherein few select states can mask typical behavior. Here we implement a continuous family of tunable C-phase gates on an array of superconducting qubits to experimentally observe an eigenstate-ordered discrete time crystal. Here we implement the continuous family of tunable C-phase gates on an array of superconducting qubits. Okay, so they're just saying they're making a quantum program, basically, using C-phase gates, which I don't know what they are. Hopefully they explain that. On an array of superconducting qubits, which just, it just means qubits for the sake of understanding. To experimentally observe an eigenstate-ordered discrete time crystal. Okay, so still don't know what that means, but they're going to make a discrete time crystal. They think they're going to physically actually make one on their quantum computer. We describe the characteristics, spatiotemporal response of a discrete time crystal for generic initial states. Okay, so I guess they're just saying they're going to explain how these things evolve generically or something. Or they're going to say that they see that they evolve the way they expect or something. Our work employs a time reversal protocol that discriminates external decoherence from intrinsic thermalization. Okay. And leverages quantum typicality to circumvent the exponential cost of densely sampling the eigenspectrum. Our work employs a time reversal protocol. So I don't really. This has always actually been something I've been confused about. Is what thermalization actually means. I thought that it was basically general decoherence, or generally. Yeah, I didn't think these things were really different. So, okay. Hopefully, I can get a better idea when I actually read what they did. And leverages quantum typicality, I've never heard that word before, to circumvent the exponential cost of densely sampling the eigenspectrum. Okay, this I think I kind of understand. So if you want to actually know the state of your quantum system, you need to make like a ton of measurements, basically, like exponentially many measurements. So that's what they mean, exponential cost, exponential in the number of qubits. In fact, there's 2 to the number of qubits measurements you need to take, if I recall correctly. So I guess they're saying somehow they're going to figure out the state without having to densely sample or something. In addition, we locate the phase transition out of the discrete time crystal with an experimental finite size analysis. Okay, these results establish a scalable approach to study non-equilibrium phases of matter on current quantum processors. All right, that was the abstract. Okay, hopefully, I think maybe kind of understood like 60% of this, 50% of this. So that's not too bad. Let's keep going. In an equilibrium setting, quantum phases of matter are classified by long-range order or broken symmetries in low-temperature states. In an equilibrium setting, quantum phases of matter are classified by long-range order or broken symmetries in low-temperature states. Okay. I didn't know that that was always true, but this is... in equilibrium setting, quantum phases of matter. Long range order. So long range order is just what I was talking about before, the long correlations. Or broken symmetries. Okay, I'm not sure why broken symmetries. So let's look at figure 1. Order and eigenstates. A. Equilibrium phases are characterized by long-range order in low-energy eigenstates of the time-independent Hamiltonians. E.g., an Ising ferromagnet with a pair of degenerate ground states that resemble Schrodinger cats of polarizable states. Wow, I really hate that they wrote Schrodinger cats in here. This is completely unnecessary. Equilibrium phases are characterized by long-range order in low-energy eigenstates of time-independent Hamiltonians. Okay, I'm just going to buy that this is true. I don't really know why that's true. E.g., an Ising ferromagnet with a pair of degenerate ground states that resemble Schrodinger's cats of polarized states. I mean, I think this is just saying that the ground state of an Ising model is you can either have all the spins up or all the spins down, which is true. And they're saying that's an example of an equilibrium phase. Okay. Flowcase systems typically have no ordered states in the spectrum. So here we have A. Here they're saying here's our two lowest states, which are ordered. Yeah, so I mean they have long range order, meaning that all these things are the same. So that's like long range order. So no matter which state you're talking about, they're all correlated perfectly. I guess I don't know why that's always true in equilibrium phases, but okay. And then yeah, up here you have things that are not as correlated. And then they're saying Flowcase systems typically have no ordered space in the spectrum. And B. In MBL Flowcase systems, every eigenstate can show order. In MBL discrete time crystals, every eigenstate resembles a long-range ordered Schrodinger cat of random configurations of spins and its inversion with even odd superposition split by pi. Okay, I'm just gonna try to keep going. I guess they're saying that like this system here, because it's on a circle, I'm guessing. So they've written up here a periodic Hamiltonian. So that means that the energy in the system is changing in time. I'm presuming that because like this is of course a special case of this, where you just have it be constant. A constant function is periodic, or at least is by this definition periodic. So I guess they're saying that these have to be things that are changing, and that when the energy is changing in the system, I guess they're saying that that basically introduces variation in what the state of the system is. And ultimately what you get is disorder or unordered. You break the long range order because like the system, I guess, like can never really get into an equilibrium or something because you're always changing the amount of energy in the system, something like that, roughly. And they're saying that there are some types of systems where you can get. So I guess they're saying these periodic Hamiltonia, and a lot of their solutions, a lot of periodic Hamiltonia have solutions that are like totally unordered. All the states are unordered. I'm assuming these are all ground states in here. Ground states at the different times. Hard to say. But I guess they're saying there's some special ones called MBL systems that are sorry, I guess they're saying there's some that are called MBL that do have ground states or whatever, these states that are have this long range order. But what's weird is this, what they've written here as saying that like having this anti-symmetric combination of states gives you this unordered thing, but then the symmetric combination gives you an ordered thing. Maybe that's really simple, but that doesn't ring any bells for me right now. But okay. Yeah, so anyway, there's kinds of a lot of times in normal systems you have ground states that exhibit this long range order, meaning that the state of the system locally at some point is going to be like perfectly correlated with the state somewhere else. I guess if you have a periodic Hamiltonian, they're saying that that normally doesn't happen, but then there are some systems where it does happen. That's all I really got from this. All right. Many body localization. I see. In the presence of many body localization. That was what MBL stands for. However, I was up here. An equilibrium setting, quantum phases of matter are classified by long range order or broken symmetries in low temperature states. The existence of ordered phases in periodically driven Flowcase systems, on the other hand, is counterintuitive since energy is not conserved. All right, let's we keep talking about Flowcase systems. I want to just quickly go down here. Are they going to like give me what are the sections here? This paper is actually pretty short, so I'm assuming they're not going to like really go into this, what this Flowcase system is. Just got to know. C-phase gate implementation. Flowcase calibration. Flowcase calibration. Derivation of effective Hamiltonians. Spectral averages via quantum typicality. Okay. more stuff. That's weird. They have two. Oh no, they just like, it's just attached twice. Okay. All right. Let's see if we can quickly. Let's not waste a ton of time on this, but quickly just understand what a Flowcase. What was it called? Flowcase Hamiltonian or Flowcase system? Flowcase Systems. Driven quantum systems. This is too in depth. I want like the 1,000. Flowcase. Systems that spontaneously break time to entry. Okay. Haven't found anything easy, so let's see if we can keep going without it. But generally, I mean, this thing, kind of just scanning this seemed to give me the right idea. Okay, I guess I can at least read the introduction. During recent years, we could bear witness to immense research activity, blah, 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 in particular development, laser and maser systems. An atom continuously exposed to an oscillating field eventually ionizes whatever the values of the angular frequency omega and the intensity I of the field is. The rate at which the atom ionizes is dependent on both the driving frequency and the intensity. Interesting enough, in a pioneering paper by Rice, that's seemingly paradoxical results extrapolates that extremely strong field intensities lead to similar transition probabilities and more modest intensities, i.e. one observes a declining yield with increased intensity. This phenomenon of stabilization that is typical for the threshold. Get to the Flowcase, man. Other activities that are in the limelight of current research are control of quantum processes, the selective control of reaction yields products in chemical reactions by use of a sequence of properly designed coherent light pulses. Our prime concern here will focus on quantum dynamics of driven bistable systems. Such systems exhibit an interplay of three characteristic components: 1, nonlinearity; 2, non-equilibrium behavior as a result of the driving; and 3, quantum tunneling. We shall approach this complexity of driven quantum systems in a sequence of steps. In section 5.2, we introduce the archetypical time-dependent interaction schemes. Section 5.3, we introduce the reader to tools for something or other. Is this about Flowcase? This isn't about, I see. Crap, I should have just came down here. I'm very stupid. With intense fields interacting with the system, it is known that semi-classical theory, between the fields of classical theory, provides results that are equivalent to those obtained from a fully quantized theory whenever fluctuations in photon number can be neglected. Here we should be interested in investigation of quantum systems with their Hamiltonian being periodic function in time. The symmetry of the Hamiltonian under discrete time translations, blah blah blah. Discrete time translations enables the Flowcase formalism. This formalism is an appropriate vehicle to study strong linear periodic systems. Okay, so it seems like Flowcase systems are just literally defined by this. With this respect to periodicity of perturbations at all levels of approximation, but its use intrinsically avoids the occurrence of so-called secular terms. Terms that are linear or periodic in the time. Terms that are linear or not periodic. Okay. This is also a little bit weird because, like I said, constant Hamiltonian is, of course, an example of this. And most, anything time dependent can be broken into Fourier series. So, like, you should always be able to kind of approximate the Hamiltonian as a bunch of periodic Hamiltonians, but I guess that wouldn't, the whole Hamiltonian wouldn't be periodic with one period in that case. Okay. So presumably this, a constant system is also a Flowcase system, but anything that has a periodic Hamiltonian. All right, dynamics. So however, what was I? Since energy is not conserved, one expects so energy is not conserved because the Hamiltonian is changing. One expects thermalization to a featureless maximum entropy state that is incompatible with quantum order. Okay, not sure what they mean by featureless maximum entropy state, but I kind of buy that you don't expect long-range correlations. However, this heat death is averted by in the presence of many body localization, where strong disorder causes the emergence of an extensive number of local conservation laws which prevent thermalization. With the presence of many body localization. Strong disorder causes the emergence of an extensive number. So extensive. I think this is like means unrelated to the something or other. Unrelated. I don't think it's that important. Unrelated to the number of particles in the system. Or maybe related to the number of particles in the system. Where strong disorder causes the emergence of an extensive number of local conservation laws which prevent thermalization. So probably this means related to the number of particles. And they're saying that you get a bunch of conservation laws which prevent thermalization, making it possible to stabilize intrinsically dynamical phases. Dynamics in a Flowcase system is governed by a unitary time evolution operator whose eigenvalues lie on the